All right. In this section, we're now going to continue where we left off last time. Remember, last time we start off, if we give you a function, say within some interval, let's just say y equals x in some interval from 0 to 1. And we're asked to find the area. Under the curve, even though it's not a curve, but that's generally what it means. Basically, what this is saying is I want to find this area here. And we decided was the formula for the area is base times height. Or let me try height, base times width, or height times width would be better. The height itself is how high the function is from the x-axis, which is our function. And the width is what we call delta x. The formula for delta x, if all the widths are the same, is this, depending on how many intervals we want to have. Okay, so in our case, our domain is one minus 0 over n. And this first example, we see our area. The function itself is x times delta x, which is 1 over n. In this case, we only had two pieces. So our formula for the area for each segment, we have two segments in there. We have first area and the second area. So area 1 plus area 2. Now, we also discussed inscribed versus circumscribed, or lower sum versus upper sum. What's the difference? What's the difference between lower sum and upper sum? Yes. Yes, okay, I should, yes. The lower sum, it omits some of the area. The upper sum includes extra area outside. So yeah, so lower sum is what is called inscribed, which is the graph is in the rectangle is inside the graph, or circumscribed. Or circumscribed. Which is outside. So the area is inside the rectangle. So for this case, the lower sum would be the left, whether it's left side or right side, because inside each of these, we have intervals. And so on and so forth. So that's our delta x. Since we said we wanted n to be 2, so this first one's going to be 1/2. That's the first interval, starts at 1, 1/2. Then the next one starts at 1/2 and goes to 2/2, which is 1. So this is my delta x aspect of it. It's important to define the upper and lower before you start. Because if we did the lower sum, that means we're going to take the part of the rectangle that has less area. In this case, it would be the left side of the intervals. In this case, it's left side. The upper sum would be the right side. Understand, what do I mean by left side, right side? Is we have an interval. So is it on the left side or is it the right side? Is it the smaller end or the larger end? That's what that's saying. So if we use the lower sum in this first one, for area 1, we have f of 0 times 1/2. That's your delta x. Because your area is your function times your delta x. And our delta x we're saying here is 1/2. And our function is just x. So the left end, the lower sum of x value of this interval is 0. So it's 0 times 1/2, which is 0. That's my first rectangle. The second rectangle, the lower bound, is 1/2. So it's f of 1/2 times 1/2. So it's 1/2 times 1/2 is 1/4. So my total area is the sum of those two. So 0 plus 1/4. The area is 1/4. Now the upper sum. Now we'll look at the right-hand side of each of these. Instead of 0, I'm now using the right-hand side. In this case, it's 1/2 times delta x. The delta x is still 1/2. So 1/2 times 1/2 is 1/4. Then the next area of the second one, it starts off at 1 times 1/2. So we have 1 times 1/2 is 1/2. Add the two areas together. 1/4 plus 1/2 is 3/4. So this is important because we have to understand the concept, the terminologies. When we say upper sum, lower sum, left bound, upper right bound, this is what we're talking about. We have to understand the picture itself. So we know if we say the lower bound, it's which part of the interval will give us the lower value, will give us the inscribed graph. Which side of this interval will give us the outer graph? So that's what we have to know, because we'll get to questions where it says, find the lower sum, find the upper sum, lower bound, upper bound. Now, the problem with this is to make this more accurate, what do we have to do? To make finding the area of this graph more accurate, what would we have to do? Smaller intervals. So the more intervals we have, the more accurate our value becomes. So basically what we're looking at is as our delta x goes to 0, as the width of our intervals goes smaller and smaller and smaller, what does that mean happens to our graph? I mean, our calculations. Well, it gets more precise, but there's a lot more of them. So the smaller these intervals become, . the more of these sub areas, these subdomains that we have. That's where this next section starts off with. This section deals with finite sums and the sigma notation. Depending on whether you're reading it in Latin or Greek, this letter has two different names. How would you read it?
The Greek symbol for sigma.
Well, yeah, that's yes. What's the Latin word for it? Latin, Greek. And it would be more precise if they used the Latin version, but they decided to use the Greek. This is the sigma notation for the symbol represents summation. Because if we had f of x, and it's made up of, like we just had earlier, area 1 plus area 2 dot 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 plus area n, depending on how big n is, that's a lot of writing to do. So that's why we use this symbol here. Let's make it x sub I. Well, let's make it f of I. F of I. This is our index. The index starts off from 1 and goes to whatever value n we want it to be. So what this would be was f of 1 plus f of 2 dot 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 plus f of n. You always start off with the initial index and end at the terminal index. And it doesn't have to be just of numbers, it could be of functions also. And it doesn't have to start at 1. I can start at 0 if I wanted to. Let's work this one out. What would I write first? What would this represent? So what's my first I? So I put, in place of I put 0 squared. And since it's a summation symbol, I add the next one. What's the next index? 1 squared. The next one is 2 squared. Because I'm indexing I. That's the base. The next one is 3 squared, then 4 squared, and then 5 squared, which is where I stop, because that's my last n I'm looking at. 0 squared is 0, 1 squared is 1, 4, 9, 16, 25. It's 55.
Professor, I have a question.
Yes.
I don't see a notation stating what the step value is. Is it always whole numbers? Are there decimal
It's integers.
points?
Yes, it's integers. Because this is a counter, because it has to be integers because between 0 and 1, there are an infinite number of numbers. So since this is a counter, it's only integer. Actually, it's only whole numbers. Very, very rarely, if ever, do you ever have a negative number in there. And it doesn't have to start, you don't have to use I, you can use K, you can use any letter you want to. And it could be equations as well. Let's say I is equal to 1 to 3, 5I plus I squared. We can do equations as well. Don't look around. It'd be easier if you look. I must stop giving you those things. Those things are too much of a distraction for you. It's listen to that. So how would I do this one?
Or then I for function. Is this just like continuous function?
Yeah, it's repetitive, yes. So in the first one, I is 1. So for the first one, anywhere I see an I put a 1 in its place. Then I add the next index. After that is 2. So anywhere I see an I put a 2. Then the next one is 3, and that's also where it stops. So once I put the values in there, I work them out. 5 times 1 is 5. 1 squared is 1. 5 times 2 is 10. 2 squared is 4. 5 times 3 is 15. 3 squared is 9. 6 plus 14 plus 24. I don't need the parentheses. 6 plus 24 is 30. Plus 14 is 44. And we have to know how these work because it goes both ways. I can give you a function with a summation and you work it out. Or we can work conversely. I can give you the results of it and you can tell me what formula created that sequence. So let's look at example 1. The first one. Summation of k starts at 1 and goes to 5 of k. So what would you do there? All it is start with the 1, then go to the next one, then the next one, and all the way up till you get to 5. Six plus 6 is 12, 13 is 15. Summation of k equals 1 to 3, negative 1k times k. And literally all it is in each one of these intervals, anywhere you see a k, put a 1 in the first round. Negative 1 to the power 1 times 1 plus the index go to the next one. Negative 1 to the power 2 times 2. I keep on going until I get to 3. Negative 1 to the power 3 times 3. And you work out each calculation separately. Negative 1 to the first power is negative 1. times 1. Negative 1 squared is 1 times 2. Negative 1 to the third power is negative 1 times 3. So it's negative 1. 1 times 2 is 2. Negative 1 times 3 is negative 3. So we have negative 4 plus 2 is negative 2. Summation of k equals 1 to 2, k divided by k plus 1. So in the first iteration, start off with k equals 1. Anywhere I see a k, I put a 1. Plus the next iteration, k equals 2. And that's where I stop because k is equal to 2. So we get 1 over 2 plus 2 over 3. Add the 2, we get 3 plus 4 over 6. So it's 7 over 6. And the fourth one, k is equal to 1 to 5. K squared, k minus 1. No, it's not 1. It starts at k is 4. Why could we couldn't start off with k as 1? Because the first one would be undefined. So the whole thing's undefined. So the first one, it's 4 squared over 4 minus 1 plus 5 squared, 5 minus 1. 16 over 3 plus 25 over 4. That's 75. 64. So 64 plus 75 over 12. So 139 over 12. Very straightforward. Not much to it. See the next example. Now we get to work backwards. Example 2 says express the sum of 1 plus 3 plus 5 plus 7 plus 9 in sigma notations. So the first way we could do it, remember, k can start at any way you want to. You can start off at 0, you can start at 1, 2, 3, 4, whatever. So if k starts at 0, then we have 1 plus 3 plus 5 plus 7 plus 9. This is my index. K is equal to 0, 1, 2, 3, 4. So creating a k starting from 0, so it's 0, 1, 2, 3, 4. So it goes all the way to 4. That tells us that part. Now we got to put the equation in there. What equation can we put in there that when k is 0, it gives us 1. When k is 1, it gives us 3. And when k is 2, it gives us 5. And so on and so forth. Well, we can't just put k plus 1. If we put k plus 1, then that one will work. But this one will not work. It's supposed to be 2 for this one. How about 2k minus 1? No, 2k plus 1. 2 times 0 plus 1. 2k plus 1. 2, yeah. Because when x is 0, it equals 1. When x is 1, it equals 3. When k is 2, it equals 5. 2 times 3 is 6, plus 1 is 7. So there's your formula. When k starts at 0. When k starts at 1. Remember, we want to go 1, 3, 5, 7, 9. This is k equals 1, 2, 3, 4, 5. So k starts at 1 and goes all the way up to 5. We can't use the same one here because 2 times 1 is 2 plus 1 is 3. 2 times 2 is 4 minus, so we can do minus 2k minus 1. 2 times 1 is 2 minus 1 is 1. 2 times 2 is 4 minus 1 is 3. 2 times 3 is 6 minus 1 is 5. That's it. So you have to be able to go both ways. You have to be able to find an equation that fits the pattern, the sequence. What if k equals, the beginning was negative 3? We want 3, 1, 3, 5, 7, 9. So this first one, k is negative 3, negative 2, negative 1, 0, and 1. So our summation symbols will start off with negative 3 and go all the way to 1. So when k is negative 3, in the first round, answer has to be 1. So negative k minus 2. Negative k minus 2. Let's try that. So negative is 3. 3 minus 2 is 1. When k is negative 2, no, negative 2, that'll give us 0. That wouldn't work. That one won't work. All right, so we'll look at another one. So negative 3 to 1. K plus 4. So negative 3 plus 4 is 1. 4 minus 2 is 3, 2, not 3. So k plus 4 wouldn't work. Okay, 2k, negative 6, negative 6, 2k, give me negative 6, negative. So if I have 2k, if I make it negative 2k, negative 2 times negative 3 is negative positive 6. Minus 5. Let's try that. 6 minus 5 is 1. The next one is negative 2. Negative 4 minus 5 is negative, wrong way. That one won't work. So that one's going the wrong direction. So I got to do plus. So I got to do positive. So I have to add, if I add 5, that's negative 6 plus 5, so it's 7. Negative 6 plus 7 is 1. Negative 4 plus 7 is 3. Negative 2 plus 7. That's it. You will be faced with equations that way. You do have to figure out what happens to them. You may have to come up with a formula that satisfies it. The properties of sigma notation. The sum property. I had a summation from k equals 1 to n of 2 terms. I have a sub k plus b sub k. That's the same thing as taking each one separately. And the proof of these are pretty straightforward. Because if we had this, let's say it went from 1 to 3. So what we would have would be A1 plus B1, A2 plus B2, A3 plus B3. I don't need the parentheses. By the commutative property, I could put all the A's together and then all the B's together. So that's why I have those separately. So it's the same with all of them. It's by using the commutativity and associative properties. So the sum rule says that. The difference rule says the same thing. Instead of a plus, I have a minus. The difference rule says A sub k minus B sub k is equal to the summation of A sub k minus the summation of B sub k. It's understood right now. You don't have to put the subscripts because it's understood that your subscript will be k since that's what's over here, and usually starts at 1 and goes to n. So instead of writing those all the time is shortcut. We just leave them like that. So if there's nothing there on the top and bottom, it's implied that it's k equals 1 to n. The constant multiple rule. But the constant multiple rule says if I have some constant number multiplied to my index term, I get that if I expand it. And since all of them have a c in common, I can factor out the c. And then I have my summation. So if you have a constant multiple, that constant multiple can go out in front and then take the summation of whatever you have and then multiply it by the constant at the end. The constant value rule. What does that mean? If it's not indexed, remember the index, you have to have, for example, you have to have a k in the equation for it to be indexed. If it's just a number and you have this summation symbol from k equals 1 to n, that means this number here is added to itself n times, which is exactly what the definition of multiplication is. So if you have a constant term that's in the summation symbol, then take the n value and multiply it by that constant term. Because it says that that constant value is repeated itself n number of times. Okay, so using these rules, the summation of k is equal to 1 to n of 3k minus k squared. How would you expand that one? Well, first off, we have a difference rule. Minus that's the first one. Is the difference rule. Then we have a constant multiple, so it goes out in front. And there you have it. That's using the properties of sigma notation. And the next one. Summation of negative a to the base x. So it's indexed from 1 to n. What do you think you do in this one? The only thing that's indexed is this. So what about the negative?
Constant.
It's the constant, because a negative, all a negative is you're multiplying by -1. So that means that negative can go out in front. There you have it. K equals 1 to 3, K plus 4. Let's go ahead and use the rules. So what rule do we use in this one? The sum rule. So this first part is just K from 1 to 3. So it's 1 plus 2 plus 3. And what do we do with the second one? Using the properties. It's,
It's the constant, so it's
yeah, it's just constant. So it's multiple. It's the constant times the number of iterations, n. So it's 3 times 4. So it's 6 plus 12 is 18. K equals 1 to n, 1 over n. Is there a k in this equation? No, so it's just a constant. We do the same thing we did before. So we take 1 over n times how many times it occurs? N. The n's cancel, so the answer is 1. So far, so good. Now, this concept was invented and demonstrated about 250 years ago by a gentleman named Gauss. He was an 8-year-old student in a classroom, super smart, in a high school class. And the instructors were getting tired of him always correcting them and giving them answers. So to punish him, the teacher says, okay, go outside and don't come back until you add up all the digits from 1 to 100. He came back about 5 minutes later with the answer, which upset him even more. This is how he did it. He looked for patterns. So let's look at the first basic ones. 1 plus 2 plus 3 plus 4. If we only had 4 numbers, what would that sum be? If we add them all up, what would that be? How about 1 plus 2 plus 3 plus 4 plus 5 plus 6? What would that be? He started noticing, okay, is there a pattern here? He goes, yes, there is. How do we get 10 from these? If we look at the numbers, the beginning number and the end number is the same thing as the next ones. So that sum, so 5 times 2 is equal to 10. Let's look at this next one. 1 plus 6. We had 7. 7 times 3 is 21. But the question he had next to himself was, where do these numbers come from? Well, 2, how many numbers do we have here? 4. If we divided those, since we're going pairs, if we divide them by 2, then that's where we get the 2. In this one, we have 6 numbers, and we pair them up, we have 3 pairs of numbers. So what he did was the sum of first plus last times the number of pairs. Because you notice every one of these pairs, as we go down, all equal 7. So 1 plus 6 is 7. 2 plus 5 is 7. 3 plus 4 is 7. So they're all made up of 2 numbers. So if we have 6 numbers, that means we have 3 pairs. How do we do that? We have the first and the last. So A plus B, and then n divided by 2. Which become n times A plus B over 2. Which, since only deal with n's, the n is the number of elements you have. You start off with 1, the first one, and you add the nth element, and there's your summation. That is the formula he came up with, is if we added all those together. Now, this is important because we have to know this formula. Whenever you get an equation and you're left with summation of k, 1 to n, you can replace it with this value. Why would we do that? Well, because we know what n is. We can plug it in there. Now we have a value. Likewise, if we had the summation of k equals 1 to n of k squared, this can also be written as an equation. So whenever you have k squared, you simply write that equation in its place and plug in n for that value. And k cubed is n plus 1 over 2 squared. Put the last one on here also. Because we'll be using these formulas a lot, actually, in some of our homework and stuff, questions like that. So far, so good?
Yes.
So what we're looking at here is, remember, all this stuff is combining what we did earlier is, why do we have to have the summation? Because we want to add all of these smaller and smaller rectangles. And the number as the rectangles of this, as the rectangles of this object get smaller and smaller and smaller, we have a larger n value. So here's the dichotomy of it. We want more rectangles, right? So that means we need n to go to infinity. If n goes to infinity, what happens to the size of each rectangle? Eventually goes to 0. As n goes to infinity. Because now we have to look at, because we're going to put all these stuff together, because what we're looking for is we want to discuss the limit. As n goes to infinity, we want delta x to go to 0. But this is not the formula of it, but this is eventually we're going to start putting these two pieces together. And that when that happens, we can start solving a lot more problems. Example 5. Find the limiting value of lower sums. That's important. Approximation to the area of the region R below the graph of f of x equals 1 minus x squared and above the interval 0, 1 on the x-axis. Using equal width rectangles. Whose widths approach 0 and whose number approaches infinity. There's a lot of important information in that sentence, in that paragraph right there. This is the hard part about, the hardest part about calculus is being able to read what's given to you in these sentences. First off, do we know what the graph looks like? 1 minus x squared. Well, we know what x squared looks like. That's a parabola. What does negative x squared look like? X squared is like this, negative x squared is down, and a vertical shift of one space up. So it looks like this. It goes to 1 up here, and it goes to 1 down here. We only want it on the first quadrant, so we're only looking for this area here. Why is that? Why is knowing the graph important? That's the only way we can determine if it's lower. Well, not the only way, but the easiest way. Otherwise, we'd have to take the values and plug them in there, see what gives us a lower number. Right, and we're looking for the lower sums. So that means our input values will be on the side of the intervals. Each of these intervals go from, it starts off at 0, and it goes to delta x, to the first delta x. Then the next one starts off at delta x and then goes to the next point. This is delta x1, then it goes to delta x2. Does it say anything about delta x in the statement? Delta x, equal with. Since it says equal with, that tells us that delta x is given by the formula b minus a over n over the entire interval of our domain. Because if it was different sizes, then it would have to give us those. What else is it telling us? Whose number approaches infinity. So that's saying as n goes to infinity, what happens? The width, delta x is the width, it goes to 0. So what are we looking for in this whole thing? What are we looking for actually? Of because remember, a limit doesn't work because a limit is just the LIM part. What's the f of x part? What does that find for us? What is the equation part? Area. So what's the formula for area? Base times width. Okay, so what's the base? No. Think about it. What's the base?
X squared. That was nice.
No. The base is delta x. Because remember, we're looking at the rectangles, areas of the rectangles. Each one of these we have to find the areas of. We have rectangles. So do we have the height? How do we find the height value?
That's our f of x.
Yeah, that's f of x. The distance from the x-axis to the graph is f of x. So areas are f of x times this is the height, times the base. The base is delta x. Do we know what delta x is? Remember, we have our function is f of x. That's 1 minus x squared on the domain of 0 to 1. So what is our delta x? B minus a over n. So what is b? What is a?
1 minus 0?
Yeah, because whenever we talk about closed intervals, we're always talking about going from B to A or A to B. So A is 0, B is 1. So our delta x is equal to 1 over n. So because of this, each one of our rectangles that we have, so the first interval will go from 0 to our first interval, 1 over n. The next one starts off at 1 over n, and it goes to the next one, which is 2 over n. The next one starts off at 2 over n, and goes to 3 over n. And it keeps on going to n minus 1 over n to n over n, which is 1, which is our endpoint. So these are our delta x's. They're all equal width. Now, in each of these, since we're looking for the lower sums, which one of these values is going to give us a lower sum, the left or the right?
The left.
Are you sure? Look at the picture. If we use left, how can that be the lower sum if it's above the
Oh,
picture?
0, 0. I mean 1. 1 over n.
So we'll have to use the 1 over n. Our delta x we'll be using is 1 over n. It's going to be the right-hand side. So we're going to use 1 over n, then 2 over n, then 3 over n. Those are each one of our values that we're going to be using in our function. Because the area is f of x times delta x, which is f of 1 over n times delta x is 1 over n. This is for the first one. That's for the first interval. Then for the second interval, we have f of 2 over n times 1 over n plus f of the next one is 3 over n times 1 over n, and so on and so forth. F of 1 over n. So I'm using the right bounds. So this, instead we're going to put 1 instead. All right, so this is how we build it. Because now, if you look at this area function can now be represented by a summation symbol. Where k starts off at 1 and goes to n. So what's the only thing that changes in this formula, in this pattern here? Right. So it starts off at 1, then 2, then 3. So that is, if you look at it, that's our counter. Which is times delta x, which is k is equal to 1 to n, f of k over n, delta x is 1 over n, What is f of x? Remember, f of x was our function 1 minus x squared. So our summation is 1 minus x squared. And x is whatever's inside the parentheses. So it's k over n squared times 1 over n. Inside here, I have 1 minus k squared over n squared times 1 over n. This becomes the summation of k equals 1 to n. Distribute this of 1 over n minus k squared times 1 is k squared. N squared times n is n cubed. All right. Now, what property do we use here? The difference rule, not difference quotient. So we have the summation. Let me write that again. As k equals 1 to n of 1 over n minus k squared over n cubed. So this becomes summation of k equals 1 to n, 1 over n, minus summation k equals 1 to n, k squared, n cubed. Remember, so the first one doesn't have any k values in it. So how do I simplify this one? Because once we define what n is, this is just a constant term, right? So it's 1 over n times n, since it's a constant value. The only variable we have that changes is k. All right, so then we have, since n is a constant, it's a constant multiple. I can bring it out in front. Why did I do that? Well, 1 over n times n is 1. What is the summation of k squared? Summation of k squared is this equation here. N times n plus 1, 2n plus 1 over 6, not n. This is 6. Now simplify it. N cancel. So we have n plus 1, 2n plus 1 over 6n squared. Let's multiply these out so see what we have. So that becomes 2n squared plus n plus 2n plus 1 So it's 2n squared plus 3n plus 1. 1 minus 2n squared plus 3n plus 1 over 6. Remember what the question said. We want these widths to go to 0, which means n has to go to infinity. Which means we now take the limit as n goes to infinity of our equation. So what happens inside here? Again, this is a difference rule. So we have the limit as n goes to infinity of 1 minus the limit as n goes to infinity of this whole monstrosity. We talked about this not too long ago, last chapter, or chapter 4. What do we do with this equation as n goes to infinity? We could, if we expanded this, we would get 2n squared over 6n squared plus 3n over 6n squared plus 1 over 6n squared. N squares cancel, so we have 2 over 6, which becomes 1/3. 3 and the 6 cancel, so we have 1 over 2. Take care of one of the n's. As n goes to infinity, these values go to 0 because they become infinitely small. So the limit of 1 is 1 minus the limit of 1/3. So the answer is 2/3. So that's the area under the curve. Well, it's long term because I had to go through each step. I mean, had everybody remember all their algebra formulas and shortcuts, we could have skipped half of these steps. But don't ever do that. It's much easier to write down each step that's going through, so you see if something goes wrong, you can easily see it. Basically, what this is looking for is the horizontal asymptote. As you have the limit as n goes to infinity of this function here, it's the horizontal asymptote. Just look at the leading. Forget anything that's not the leading term. Just look at the leading term. The n's cancel, the n squares cancel. 2 over 6 is 1/3. But I had to show you what all went on. So that's the lower sum. Would it be different if we did the upper sum? Ooh, good idea. Anybody agree with that? The statement was it had to be larger if we did the upper sum. It would be true, but all of our rectangles became infinitely small. So all of our delta x's became infinitely small. So therefore, that's a great idea you had there. But because of that, the upper and lower sum are equal. which is where we left off yesterday. Remember, we left off yesterday. We did that one equation, actually that same equation, but we did it with 2, 4, or 6 intervals. When we did that, then you have a lot of open space. Even did the midpoint, that's still not going to be good enough. So far so good. Which now, because of this, that leads us to what we call the Riemann sum, which is the important part, which will help us define the fundamental theorem of calculus. The Riemann sum. Basically, it's this. It's a procedure. Here are the steps. First step. You have to make sure that f of x is bounded on a closed interval. Second step. Subdivide f of x, or subdivide the interval that we're dealing with into equal intervals. In general, it doesn't have to be equal, but we're saying for our case, we're going to look at it and start off with equal intervals. And we'll talk about a case where it's not even intervals. So what's happening here is this. Remember, it has to be within A and B. So A has to be less than the first interval, the second x, the third x. Because what do A and B equal in this whole thing? A would constitute, in this case, it's the initial one, so it's the initial x value. And then B would be the x sub n, the last value in the sequence. Third step. So we have an n number of sub-intervals where each interval is like from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4. That's each interval. So that way we can pick whether we do the upper or lower sums. Form the sums of the approximation. What does that mean? Define each of those values, whether you use upper or lower bound. And that's what you're trying to get to here. Choose n minus 1 number of points. And place in increasing order. Note, these x intervals are called partitions. Those are all your points. You put them in increasing order. Again, from these, we'll create our intervals, x1 to x0 to x1, x1 to x2, x2 to x3, so on and so forth. So if all the widths are the same, it doesn't matter. But if widths are not equal, then use the norm of P. Norm of P. It's designated like that. That's the norm. Which equals the largest subinterval. Why would you use this largest subinterval? Remember, if you have n number of intervals and they're not equal size, why would you use the largest of those intervals as your value for delta x? Remember, if the width of delta x, if they're not equal, then use the norm. Why would you? Because if you use the smallest one, can the smallest one approximate anything bigger than it? Case in point, let's say the statistics. If I just interviewed this class, can I make an assumption about all students at Dallas College? It's too small. Well, I don't know. It's just because the sample is too small. It's not even 1/10%. So I would have to use a larger. I would get a better idea if I used the largest class, a class that had 50 students or 60 students. So the wider the delta x is, the more you can approximate anything smaller than it. So that's how we choose our delta x. So let's see, where's an example? Yeah. So our partitions, so it subdivides our interval into n closed and sub intervals. So our delta x becomes x sub 0 to x sub 1, x sub 1 to x sub 2, x sub 2 to x sub 3, and so on and so forth. Now, when we look at this, do all the values have to be positive? When we find these areas, do all of them have to be positive? Can I do that?
What do you mean by like positive or negative? You're adding something, looking for an area is a material thing, then it has to be positive. But if you're looking at negative space, even then I would make a negative space positive.
Positive and negative is always relative. in this case, what would, if you graph it, what would positive be? Above the x-axis, what's negative? Right, so it's again, it's all relative to how you define it. So yes. Why is that?
Well, because like the one that's below the axis is still like a value, even if it's beneath that. It's like what you said, it's.
Okay, you go on.
I can't go on that, I mean, like, just philosophically, if you're measuring something,
No.
even if it's below, since it doesn't make it negative, it still takes up that space, because negative space is still space. So can area be negative? Yes, that's really the question. How can area be negative?
Remember, this is made up of a function.
It's like a half a split of DNA.
So if I said the function was cosine, and at 2 pi, or at pi, what is cosine at pi?
How do you put the unit circle?
Yeah, because you do unit circle. Here's 0, that's at 1. This is at 0, 1, so at pi over 2, it's 0. And at pi, it's negative 1. So now, if I had at f of pi, that equals negative 1. So my area at pi and 1 over 2, let's say 1 over 20, this will give me area of negative 1 over 20. So it is possible. Again, it's relative, because your function has to be defined relative to the x-axis.
We stay in the direction of the.
Right. That's exactly what it's saying. Yes. It's relative to where it is. Now, we'll get to a point where we'll see that it doesn't matter if it has, but it has a huge dramatic. Think of this cosine from negative pi to pi. So I'm going from negative pi to pi. What would the area of that function be?
Yes, based on this exercise, it's the area underneath.
It's this area here, and this area here. Why would it be 0?
Oh, because it's the two halves they
That equal, yes, because
so then that's like the area of movement then. That's not like static area. So you
it's
have to,
not like we can't compare movement and physical attributes. Because in movement, you're talking about forward and reverse. Do they cancel each other? Yeah, you end up at the same place. That's what's happening here. In physical space, if I borrowed $80 and I paid back $80, how much am I in debt now? 0. The same as if I go forward 80 miles and then back 80 miles, haven't made any progress. So think about it, your cars that you have 100,000 miles on it. You always park it in the garage. So after all that time, the 100,000 miles, and you never even left your house. In essence, that's what's really happening. That's what it's saying. Let's look see find an example here. No, we'll get the next. But this is important because you have to be able to define positive and negative values when it comes to areas. It is possible to have negative areas, as we've just seen. Okay, the set was partitioned into 0, 0.2, 0.6, 1, 1.5, and 2. Is a partition of this closed interval. What would that be? Nope. What does that symbol represent?
Largest difference?
The largest difference. Well, we don't know yet. Because we'd have to first go, how many intervals do we have? We're going from 0 to 0.2, 0.2 to 0.6, 0.6 to 1, 1 to 1.5, and then 1.5 to 2. Well, yeah, so this one would be 0.2, this one would be 0.4, this one would be 0.4, this one is 0.5, and this one's 0.5. So the norm would be 0.5. So that would be your delta X you would use. Because you can't have a different ones on all of them, so you have to pick the one you're going to use and use it. So that's use the largest one. Oh, I'll give you a formula for it. The Riemann sum. Okay, equals 1 to n of your function. This is for the right-hand side, the upper bound. K times b minus a over n times b minus a over n, which is our delta x. Let's see, maybe we'll skip one. Now, this is a general form of the Riemann sum. F of x is the height of the function. Let's say we have this interval here, x3 to x4. We're looking at this area here. What this one says, C of k is any point inside that interval. What it's saying here is you're not restricted unless you want to find upper and lower. That's the only time you need the upper and lower bounds. Other than that, you can pick any point you want to inside that interval. That's what that says. And delta x is, if it's equal sizes, it's this. If it's not equal sizes, then it's x n plus 1 minus x n. So it's the bigger, it's the upper bound. In this case, it'd be x to the 4th minus x to the 3rd. So now, look at this one here. This one is used specifically on our example here, or what this one does, you start off with A. What does A represent? A represents the lower bound of our interval. Once you get this, so what this one's saying is in my interval, A is here, A plus K 1 over N is here. So with this one, it starts with this one goes to the right-hand side. Why is this one different than the left-hand side formula? Because left-hand side formula starts off where? It starts off at A and then goes to the first delta X. I don't need this part. I start off on the left-hand side, I start with A. This one tells me I have to start with this one. Is it making sense? I'm looking at you guys, you just saw a three-headed donkey. I mean, it needs some, to me, it makes a lot of total sense. But I don't know if it's making any sense to you guys. Here's A, here's B. Here's X1, X2, X3. The lower sum would use what for my function? What would the lower sum use? The left side. Upper sum, this is left side, it would go from A plus my delta X. Because I don't want to start off here, I want to start off there with the right-hand side. Anyway, the catcher, I can't say any different. All right, so in summary for this section, any Riemann sum with a partition of our interval, of our closed interval, gives us rectangles that approximate the region R between the graph of our function and the x-axis. And the partition with norm going to 0 would lead to collections of rectangles that approximate the region R with increased accuracy. Now, what does all that stuff mean? Any Riemann sum with partitions of A and B gives us rectangles that approximate the region. Why does it approximate the region? And what region is it talking about? Okay, what do you think region means? That's what you get from this first paragraph. I just read it out to you. Any Riemann sum with a partition of the closed interval gives us a rectangle that approximates the region between the graph of f of x and the x-axis. We partition this thing. It goes from 0 to 1. The more partitions we have, the more accurate our thing is. Whether we use the upper sum or lower sum or the midpoint or any other value in there, it gives us an approximation of the area under the curve. Here's f of x, here's the x-axis. It gives us this area eventually. That's what the Riemann sum tells us. So now, with the norm goes to 0, what does that mean? What does the norm going to 0 mean? What does that have to do with anything? What is the norm? We just talked about it 20 minutes ago. Not a difference.
I don't know if I'm answering your question, but the idea is it's more accurate if the number gets smaller, the partitions are getting smaller and smaller.
But what's the norm? That is true. Yes, that's what we're looking for. That's what we've been saying. But what is a norm?
Two lines with P and like the largest sample size, or one that's more accurate.
No. Sample size statistics.
Well, it's really, so to use the rectangle that's the largest one for the whole.
Yes.
The partition, the largest.
partition- A partition is a what?
It's a slice of the area.
Yes, yes, exactly right. So each one of these are partitions. Each of these partitions. The biggest one of these is the norm. Now, when the biggest one of them goes to 0, what happens to the smallest ones? They're already gone to 0. I mean, they're already there. If the biggest one is getting to 0, getting shorter and smaller, 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 then the little one's already there. And now what we're doing here is it will increase the accuracy of finding the area under the curve. Because instead of having rectangles, we're simply going to have vertical lines. An infinite number of them. Okay, so study up this section, learn the terminology. The terms are what makes everything important. Remember, being able to do the mechanical work of mathematics is only a small part of it. Understanding what you're doing is the most important part. The why you're doing it instead of how you're doing it. I can show you how to do it left and right, and we finish the course in 2 weeks, but it means nothing to you. What we're looking for here is what? We're looking for the actual area of under a curve from the x-axis to the function itself. And how do we find it? By partitioning that area into smaller and smaller and smaller pieces, so that eventually they become so small that instead of rectangles, they're just vertical lines. We just add them all up.
Is there a philosophy class for this?
It is a philosophy class in
It
itself.
is, but it's always like numbers, like that's why I'm asking, because like you're talking about the philosophy, but then we're always.
They're one and the same thing. In mathematics, it's the same thing. Mathematics has always been a philosophy of logic. Yes.
Here with your 40, we didn't see the difference of the partitions, like between like 42 and 44.
No, we just look for the largest one because that's the norm. The norm would be our delta x we use in our formula. Because when you do our area is f of x delta x, which delta x do you use? Because now when that one goes to 0, then we know we have everything that's smaller. We have everything incorporated now. Now, if the rectangles are not the same size, then we have a lot of issues because there's not one, you can't use this formula. Because this formula is set when all delta x's are the same. Because if not, then we'd have to input all the delta x's for each calculation we do. And that's what we did in graduate school, is we have different size delta x's, and you can analyze the curve then eventually there's the volume of the object you're testing.
Okay,
So-
so there's no philosophy of math class.
In graduate school there is.
So is it called philosophy of math?
Yeah.
Oh, okay.
You take a logic course, same thing.
Took a logic course. I didn't feel like I learned anything like this in logic.
Well, no, because it's
Like, it was a philosopher that like taught the logic class.
not a mathematician. It used to be there used to be one and the same thing. If you look at all the history books, whenever they talk about